Okay, welcome students. So today we will start lesson 41 of chapter 10 wave optics. We will discuss coherent and incoherent sources. Coherent and incoherent sources, two sources of light which continuously emit light waves of same frequency or wavelength with a zero or constant phase difference between them are called coherent sources. Now for incoherent sources, two sources of light which do not emit light waves with a constant phase difference are called incoherent sources. Now, what does this mean? Suppose your light are coming from your slit S1 and S2. Forget about this source S. Right. For now, just consider one of the light sources S1 and another light sources S2. These two sources of light will be coherent if the light coming out of these two sources have the same frequency or the same wavelength, means they are of same color. If it is a red light, then the light coming from source S1 and source S2 will be a red light, and they should have a constant phase difference, or I can say there should be a no phase difference. That means if the light comes and strike here, at the same time the light will come and strike here. If the light comes and strike here, the light comes and strike here at the same time. So there is no phase delay. Now in that case we will call it as coherent sources. Now the important point is to obtain an interference pattern, like in this case, bright, dark, bright, dark, bright. To obtain such kind of fringes, we need coherent sources only. Incoherent sources cannot produce such fringe. We'll see how. Let us consider this source S1 and S2 be incoherent sources. That means the light coming out of this one may be of different color, and the light coming out of this one will be of different color, and they will have a different phase difference. Now the important point is phase difference. As we have seen, this is the equation for the intensity of the light. This intensity, if it is a bright, high intensity, if it is a dark, low intensity, and that intensity is given by this equation. Now in our coherence case, if cos phi, or my phase difference phi, is not constant and it is continuously changing, if it is continuously changing, then the average value of a cos phi equals to 0. Now why this is 0, you will study it in your maths class. For now you can understand like this: if this phi is continuously changing, the average value is 0. Sorry. If this term is 0, then this whole term will be 0. If this whole term is 0, that means intensity I equals to I1 plus I2. Now, if intensity equals to I1 plus I2 means it will have a constant intensity. That means this one also has the intensity I1 plus I2, this one also I1 plus I2, this one also I1 plus I2, and so on. If they have all the same intensity, then in that case you won't obtain a bright and a dark fringe. So we cannot obtain a fringe using a incoherent sources. Fine. Now let's move to our next topic. Theory of fringe width. Or in this topic, we will discuss about the fringes and the distance between those fringes. Fine. Now, deduce an expression for fringe width in Young's double slit experiment. How can the wavelength of monochromatic light be found by this experiment? First, we will try to derive an expression for the fringe width in Young's double slit experiment. Now, this is your Young's double slit experiment. Okay. Now, suppose there is a narrow slit S which is illuminated by a monochromatic light. Monochromatic light means light of same color. Mono means one, chroma means color. So this source S is illuminated by a monochromatic light of wavelength lambda. If it has the same color, then it will have a constant wavelength. Now this monochromatic light is illuminating on the slit S1 and slit S2. So S1 and S2 are narrow slits which are at equal distance from your source S. Now since they are derived from the same parent source S, therefore S1 and S2 are two coherent sources which are separated by a small distance, and we will denote this distance as small d. Now interference fringes are obtained on the screen and it is at a distance capital D from your source. Fine. Now you started the experiment and you have obtained a bright fringe, dark fringe, bright fringe, dark fringe, so on. Fine. On this screen. Clear? This just represents the fringe width which is obtained on the screen. Fine. Now consider a point P on the screen which is at a distance x from the center O. Now the nature of the interference of the point P depends upon the path difference, or I can say the kind of the fringe you will get, bright or dark, depends upon the path difference. What is the path difference? The extra path that your light coming from S2 has to travel. So I can write path difference denoted by small p equals to S2p minus S1p. Now from the right angle triangle S2BP and triangle S1AP, consider your triangle S2BP. This is your first right angle triangle. Using your hypotenuse theorem, S2P square equals to S2B square plus PB square. Fine. Similarly, in your right angle triangle S1AP, this is also a right angle triangle. So S1P square equals to S1A square plus AP square. So if I take the difference of this length and this length, it should give me a path difference. So I can write S2P square, which is S2B square plus PB square minus S1P square, which is S1A square plus PA square. Fine. Now, what is your S2B and your PB? S2 B. This is the distance of the screen from the source, which is denoted by capital D. What is PB? Okay, so to understand PB, we know the two slits are a distance D, and this is the center of the screen. So this slit can be divided into two parts, each of length D by 2 and D by 2. So my PB, this length will be distance of P to O, which is X, plus this length, which is D by 2. So I can write S2B as D square and PB square as X plus D by 2 whole thing square. Now similarly, S1A square and PA square. S1A square is the distance of the screen from the source, and PA square. To find out this distance, you know the distance of point P from O is X, and this distance is D by 2. So PA is the difference of D by 2 from X. So if I subtract D by 2 from X, I will get this distance PA. So S1A square is D square, PA square equals to X minus D by 2 whole square. Now I can simplify this term. Here S2P, S1P, I can use the formula A square minus B square, which is A minus B, A plus B. So this can be written as S2P plus S1P, S2P minus S1P. And on simplifying this term, you will get twice of XD. So S2P minus S1P, S2P plus S1P equals to twice of XD. Now if I take this term to the denominator, S2P minus S1P equals to twice of XD, S2P plus S1P. Now in practical case, your point P lies very close to O. What does this mean? This point is very close to O. If this point is very close to O, let us consider it to be somewhere here. So the distance traveled by the light from S1 to O will be approximately equals to the light or the distance traveled by the light from S2 to O, and they all will be equal to this distance. And how much is this distance? Capital D. So in practice, the point P lies very close to O, therefore S1P and S2P equals to D. Therefore I can write here D and D. So D plus D, 2D. So 2XD divided by 2D. So 2 and 2 gets cancelled. So S2P minus S1P. Now this is my path difference P, the extra path traveled by the light coming out of your slit S2. Therefore my path difference equals to XD by capital D. So this equation represents the path difference equation. Here X is your distance of the point P from the center O. Small d is the distance between the two slits, and capital D is the distance of the screen from the source. Fine. Now we will discuss about the position of bright fringes, where we will obtain bright fringe. Okay, for bright fringe we have to study the constructive interference. Fine. That means for constructive interference, as we have studied in last class, my path difference should be a integral multiple of lambda wavelength. And just now we have derived this equation xd by d. So xd by d should be equals to n lambda. Or I can say this x, I can send this term to the other side, equals to, so x equals to n d lambda by small d. Now starting or taking the whole numbers, n equals to 0, n equals to 1, n equals to 2, n equals to 3. This n represents the order. which order we are taking. We are taking the 0th order, we are taking the first order, we are taking the second order, we are taking the third order. Fine. So let us start with 0th order. When n equals to 0, when this value equals to 0, in that case this whole term will be 0. If whole term is 0, that means x equals to 0. If x equals to 0, what you should get? Constructive interference. If it is a constructive interference means bright fringe. So what does your x equals to 0 means? This distance, if x equals to 0 means at the center O. That means at the center O, I should get a bright fringe. And this bright fringe is known as your central bright fringe. Fine. Now, similarly, we can do for n equals to 1. When n equals to 1, in that case, this will be 1, or I can simply write x1 equals to d lambda by d. So when this distance x equals to d lambda by d, that means your first bright fringe. In that case also you will get a maximum intensity fringe. Similarly, for n equals to 2, your second bright fringe, x2 equals to, substitute the value here, you have 2d lambda by small d. So this is your second bright fringe. Fine. So if you see the pattern 0, 1d lambda by d, 2d lambda by d, in that case I can say whenever this distance of the point P from the center is a integral multiple of d lambda by d, in that case we will obtain a bright fringe. So this denotes your bright fringe. Fine. The position of the bright fringe from the center O. Clear? Now next we will discuss the position of the dark fringe. Position of the dark fringe. So for dark fringe we have to obtain destructive interference. Again we know the path difference equation xt by capital D, and we know path difference P should be a odd multiple of twice n minus 1 lambda by 2. It should be odd multiple of lambda by 2. Or I can say from this here I can simplify x equals to twice of n minus 1 d lambda by 2d. Now we will start from n equals to 1. When n equals to 1, if I substitute this value here, 2 ones are 2, 2 minus 1 is 1. So 1 by 2 d lambda by d. At that position, I will obtain my first dark fringe. So when x equals to half of d lambda by d, at that place you will obtain your first dark fringe. Similarly, substitute the value of 2 here. 2 2s are 4, 4 minus 1 is 3, so 3 by 2 d lambda by d. In that case, you will obtain your second dark fringe. So if you look carefully, you can notice a pattern that there is a odd number 1, 3. What will be the next? 5. What will be the next? 7. So whenever your distance of the point P from the source will be the odd multiple of d lambda by 2d, in that case we will get a dark fringe, a fringe which has a minimum intensity. Fine. So that's it for today's class. In next class we will discuss about the fringe width and how we can determine the wavelength using the fringe width equation, and we will solve some numericals. Okay, so if you have any confusion, please don't hesitate to ask. I will re-explain it to you again. So thank you.